Cannonball flight. A rocket-propelled cannonball is fired from a specially equipped antique cannon located at the edge of a 28-meter tall cliff with an initial velocity of 540 meters per second and an angle of 48 degrees above the horizontal. Now, why all the words there? Rocket-propelled cannonball? I don't even know what that is. Specially equipped antique cannon? Well, we had to match this cool picture because, and here's why we've had to put rockets on the cannonball, 540 meters per second. Every meter per second is about 2.2 miles an hour, so this is a supersonic cannonball. It's like 1,000 miles an hour. But don't worry about that. The math is still fun and the problem's a good one. It's just a little unrealistic. So how much time is required for the cannonball to reach the ground? How far from the cliff will it strike the ground? What is the maximum height above the ground, that's going to be important, reached by the cannonball? Find the landing velocity of the cannonball, magnitude and direction, and then draw all these motion variables. How much time is required for the cannonball to reach the ground? And you can see what we've done here. We've stripped out all the verbiage and just put the key math things that we're going to need. So the first thing you do, resolve your initial velocity into the x and y components. And that's done here with a little bit of trig. The x component is the cosine function, the y is the sine function. Now we're going to use the second kinematics equation in y to find time to ground. That's typically the first step you take in any projectile motion problem. So here we are. Here's the equation. Final height is 0. We start at 28. We have an initial velocity. Now which one are we using here? That's the y direction. And here's our acceleration due to gravity. We have a quadratic equation. So you can either use the solve function on your calculator if you've got that working, or one of the many websites that calculate this, or do it by hand with the quadratic equation. You get two roots, and we're going to use the positive root to match the physical situation here, 81.9 seconds. How far from the cliff will the cannonball strike the ground? Second kinematics equation again, but this time in the x direction. And see right here, notice that doesn't match this, but it is 540 times the cosine of 48. That's the x direction velocity. And we find that we go out 2.96 times 10 to the 4th meters. What is the maximum height above the ground reached by the cannonball? We're going to use the third kinematics equation here in y. We weren't asked about the time, we were just asked for a displacement. And since we know the initial velocity and the acceleration, and our final velocity is going to be what? Well, at the peak, it will be 0. So it just naturally lends itself to the third equation. So we rearrange it for delta y, and we find out that the cannonball goes 8,200 meters high. But this is delta y. This is above the launch point from the cliff. And remember, we wanted the height above the ground. So y max is going to be this delta y that we just calculated, and add the height of the cliff. Doesn't really change the answer much because this thing is going so fast. It's going pretty darn high that the height of the cliff is not a big number. However, to be correct, we add it in, and we take it to the correct number significant figures 3, and we find the maximum height above the ground is 8,230 meters. What is the landing velocity of the cannonball? Well, we found the time until it hits the ground in part A, and that time, where's our time here? Time is 81.9 seconds. It shows up over here. We know that our velocity in the x direction stays constant in the absence of friction, which is what we're assuming. And then our y will be v0y plus the acceleration times time. We have a negative acceleration due to gravity. Here's our initial y velocity. And we have negative 402 meters per second in the y direction. We now want to find our total velocity. We use Pythagoras, and it's going to hit the ground at 540 meters per second. We use the arctan to find its angle. So just pictorially again here, here's the velocity vector when it hits the ground, hitting at 48.1 degrees or negative 48.1 degrees with respect to the x-axis. Draw the various motion variables for the motion of the cannonball. Let's start in the x direction. We know that the position is a linear function because there's no acceleration in the x direction, so that's this guy right here. And I use graph-free.com to make these, but you could sketch these yourselves. I mean, the slope of this line here is going to be your velocity in the x direction. And that is this graph right here. The velocity, I think it was 381 meters per second. So you can plot that. And then your acceleration in the x direction is 0. So whenever you're making these graphs for an exam or a quiz, make sure, since you're on the x-axis here, that you make it a lot darker than the y-axis, so you know that this is the acceleration. And maybe put an arrow there, and you could actually say the acceleration is equal to 0, just to make sure who's ever grading it knows what you've done here. For the y motion, we know that the position is going to be a parabola because it's a function of at squared. So that's what this is here. Again, we use the software program to design this. And you could have just figured yourself, you start at 0, you end at 0. We knew the max height, we calculated that. So you would just rough in a smooth curve there. And note over here, because of the scale of the graph, because this cannonball went so fast, we actually started above the origin here. We started at 28 meters, but you can't see it because look at the scale here. We've got, oh, let me get the pen. We've got 8,000 meters there. 28's not going to show up too well. The velocity, we start here. That's the initial velocity. It's going up, up, up. Then at this point here, which will match your peak, right? It switches. It goes to negative velocity because the ball starts coming down. So this point here matches this point here in time. And then you have a negative velocity continuing to increase in a linear fashion. And your acceleration graph, of course, is just the acceleration due to gravity, negative 9.8 meters per second squared.